Okay, so let's continue with the Feynman diagrams and Feynman rules, in particular in momentum space. So let me just remind you what we have last time. Okay, so this is the up to first order in perturbation that we could write down for this Green's function g alpha beta 1, 2, and the first diagram is the zeroth order, and second and third diagram is the first order. Okay, so let me just write down the formula for this g alpha beta 1, 2 in terms of g0. Okay, so let's look at this integrand expression for this diagram. The first term is simply g0, 1, 2, and let's look at the second and third term. The second diagram corresponds to this expression here, where we have g0, 1, 3, which is this propagator, and g0, 3, 2, which is this second half of this propagator, solid line, and a wavy line which connects point 3 and 4, which is V34, the interaction strength, and finally there's a bubble which is G044, which form a fermion loop, and because it's fermion loop we have this plus minus sign right here, and plus refers to the boson and minus for fermion. So if these propagators are made of bosons, then you don't change sign, but if they are made of fermions, then you need to change sign. There's a minus sign right there. Okay, so the third diagram is this one. So let's just go from top to bottom. So top propagator is G13 and G013, and then G034, which is the middle propagator, and finally G042. And this wavy line connects points 3 and 4, so this is V34. Okay, so later we will Fourier transform these two diagrams in K and omega space, and we will evaluate these two diagrams. Okay, so let's make a small remark. So if G0 alpha beta is actually spin independent, suppose there's no spin. Of course, this alpha and beta spin indices, but in many cases, these particles may not carry spins. Okay, so if they don't carry spins, and G alpha beta is actually spin independent, because the full Green's function g alpha beta is made of a function of all g0s. Remember, all these expressions are made of g0s and the product of g0s. So if g0 carries no spin, and all the full Green's function is independent of spin. Okay, so g0 alpha beta does carry spin, and this is actually diagonal element of 2 by 2 matrices in spin space. Then we do have this for the full Green's function. Meaning, suppose this propagator is for the same, say, electrons carry the same spin. Suppose this is spin up, or alpha beta, or spin up, or spin down, spin states. And so the G0 alpha beta is simply just G0 up, up, or down, down. Okay, so this is the simplest situation. As I mentioned, this, when you sum over this spin indices, you make a product of all these 2 by 2 matrices, right? And then you simply just take the matrix element of this product of this 2 by 2. And we could sum over the spins. This summation over the spin indices are very easy to be evaluated. So let's do it. Suppose that we simply consider the same spin propagator. Okay, and that means this G0 alpha beta is simply just proportional to delta alpha beta, and you could simply just sum over all the spin indices. When you sum over the spin indices, you get what? You get 2s plus 1 for this for the first term, because then you need to sum over the spin indices G0 mu mu. Okay, so mu is the spin indices, and so this bubble is really independent of this propagator line right next to it, because this mu and mu's actually are attached to the same propagator G0, 4, 4. As a result, when you sum over all the spin indices, you sum over this mu independently. Okay, as a result, you get 2s plus 1 as a prefactor. And for the other spin summation, since this is just delta alpha beta or same spin correlation functions, so when you sum over all the other alpha, lambda, beta, and you get 1, and this 2s plus 1 arises only if you sum over this mu for this G044. Same for the second term. Since there's no bubble for the second diagram, so when you simply use the delta alpha beta as a spin indices and you sum over all the spin variables and you get 1. Okay, so that's what you have here. So let me just put it right here. G044 is actually minus plus 2s plus 1 and 0 R4, where n is occupation number operator. So let's just Fourier transform this expression to K omega space. We follow the Feynman rules. Remember, we have this properties that this propagating lines actually merge to the same point. For here, the second diagram for the final diagram, so this propagating line is actually merged to the same line. Okay. As a result, we need to insert the convergence factor that we mentioned previously. This is convergence factor e to the I omega n prime eta, where eta is a very small positive value. So let's finish this. Okay, so this is the expression when we Fourier transform the real space time expression for this G alpha beta. And so let me just sketch this Feynman diagram in K omega space. So the double line represents the full Green's function, okay, or full propagator with the arrow, which is given by zeroth order contribution plus the first order contributions and higher order contributions. Okay, so the first propagator line is very trivial. You simply just change your variable from R tau to K omega n, where omega n is most power frequency. So that's what we have, this G0 K omega n, right? But the second diagram is the bubble diagram that when you Fourier transform this diagram, you get this kind of a K and omega n attached to all this different propagating line. So there's an incoming, say, particle carrying momentum K and multiple bar frequency omega n right here, and then the outgoing particle carries the same momentum, same multiple bar frequency. So there's no momentum transfer Q right here because K subtracted from K is 0. So Q is actually, say, K up minus K down. So it's actually 0. Okay. So in other words, if you have this bubble diagram, so immediately you see that there is no momentum transfer because the incoming and outgoing particle carry the same momentum and the same frequency. But there's a bubble right here. You can consider this as a propagating line which carried by some particles with momentum K prime and omega n prime. So when this particle actually go around this bubble and get back to this point, say 0.4, okay, right here, and so the momentum got canceled, right? So there's a particle is actually absorbed into that interaction vortex, and there's another particle actually created with the same momentum. So again, K prime, and this is K prime, so K prime minus K prime 0, so this agree with this Q equals 0. No momentum transfer that you obtained by evaluating this momentum for this propagating line on the left of the bubble. So on the left and right of this interaction potential, you get conservation momentum. Okay? And remember, the internal degrees of freedom are to be integrated over, right? So this is precisely what we're doing here. So we integrate over K prime and omega n prime for the bubble diagram. The third diagram is this kind of a self-energy loop, and you get incoming particle carrying K and omega n, but intermediate states, particle carrying momentum K prime, omega n prime, and then the final state is the same momentum omega n. So the wavy line right here actually carry non-zero momentum because Q is defined by k minus k prime, which is finite, non-zero, and also the Matsubar frequency has to be conserved right at this two interaction vortex. As a result, there is a Matsubar frequency carried by this wavy line, which is omega n minus omega n prime. Okay? And then you could simply just write this interaction U in k space as k minus k prime right here. But here, this interaction carry no momentum dependence. As a result, Q is actually 0, so you got U 0 right here. Okay? And then the spin is right here, and you need to sum over omega n prime and integrate over k prime. Okay? So this is what we will do. Okay? So in k omega space, we could perform such a Matsubara sum and momentum integration for the internal degree of freedom, and when we are done, we can actually combine these corrections together with G0, the Bayer propagator, and then this is the k omega n up to first order in perturbative expansion. And of course, we should add the higher order contributions to this full Green's function. So this is only up to the first non-trivial order. Okay, so once we just listed the Feynman diagram and Feynman rules, and it's just a matter of a bookkeeping task to simply just write down all these corrections that we need to sum over. Okay, so let's take a short break. When we come back, we will continue rewriting this expression, especially this Matsubara sum, and we could actually consider to go on to higher order term, but we don't consider this crossing or more complicated diagrams. We simply just sum over all such a bubble or this kind of a third diagram and continuously up to nth order. Okay, so let's take a short break. So please read the chapters and sections in Effective Logica. So you could see all these diagrams and this Fourier transform, the Green's function, and these expressions in Effective Logica. Okay, so let's continue. So we can rewrite this gk omega, and we defined a quantity called self-energy sigma, capital sigma, as function of k and omega n, and we insert that capital sigma in between this G0. So for this first order contributions, so there's two diagrams. So you could consider this as just some black box. So this red shaded oval represents this self-energy up to the first order in perturbation, which I marked this with superscript 1 on the capital sigma. So this represents the total contributions to self-energy up to the first order in perturbation. So you could read of this expression by considering this red oval is a sum over this two. Okay? Because this is something in between this Bayer propagator, G0 and G0 right here. So if I simply just remove this red oval and recover G0, right? So if there's no such self-energy corrections, and you simply just have this a Bayer propagator or zeroth order Green's function. But this quantity capital sigma that is inserted in the middle of this G0 just tells you that this quantity capital sigma actually modify the energy of this particle for this G0. So in other words, this sigma 1 actually correct or revise or modify the particle energy of this G0 propagator. So we will come back later for this interpretation. So that's how we call this capital sigma self-energy, because this sigma right here is actually will be added to the energy of this G0 particle. So this is the energy of this particle itself, and that is contributed from this interaction. And in other words, this is the correction from the interaction to the particle energy. Okay, so that's why we call this self-energy. So the self-energy is defined by this two internal summation or integration of this quantity that we just derived over there. And you can separate this G0 square and put it one on the left and the other on the right side of the sigma, and this is precisely what we can actually see literally by looking at this diagram right here, because this is G0, this is another G0. So if you simply just read off this diagram, and you could reproduce this expression or vice versa. So this tells you that there is a particle going this direction, and then suddenly, or in K and omega space, there is some diagrams that will contribute this self-energy of this incoming particle, and then after this scattering, you get back to this G0 again. So there's a one-to-one correspondence. So this is G0, and this is a sigma, and this is the other G0. So if I put this expressions in this way, then I can very easily see the correspondence between the Feynman diagram of the self-energy and this mathematical expression for the self-energy diagram. So these two G0s on top and the bottom, we call them this external propagators, external Lecs, because they are just out of this red box, and we don't sum over those degrees of freedom. They are external degrees of freedom, but we only sum over internal degrees of freedom, which is inside this red box. So let's keep analyzing this expression. So you know very well that when we sum over this omega m prime right here, and this capital sigma, after summing over its multiple frequency omega m prime, so this expression on the right-hand side is independent of omega anymore. So it is independent of omega n. So there's no frequency dependence. Because right here, this is the only place you have this frequency dependence, and this omega m prime, when it is sum over, the whole expression is independent of omega m. In other words, sigma 1 in this expression right here is independent of omega m. And so we could generalize this kind of a Feynman diagram, Feynman rule to higher order, but we neglect many crossing complicated diagrams and only just include this kind of self-energy sigma 1. So we can consider this kind of summation. So I imagine that I only consider this sigma 1 and the product of the sigma 1 in a connected fashion. So for example, if I consider this two bubbles, what I mean is this. We have a bubble plus this and this. So in other words, I simply just combine this single bubble right here and connect these two bubbles by a bare propagator, G0. And this is what I have done. So when I plot this diagram, this is what I mean. So there are many, many terms like this could be constructed, and of course this is just a subset of all possible diagrams in the perturbed expansion, but if we only consider this called a loop or ring diagram or bubble diagram, ring diagram, and we could consider one bubble and plus two bubbles, also three bubbles, right? Plus infinite number of bubbles. So this is what I call just kind of a approximated form to consider all order diagrams. So we throw it away many, many complicated diagrams that those propagators crossing with one another. So these are called non-crossing diagrams. So there are no crossing. So this is what I meant by crossing. By crossing, I mean this actually, if you cut the diagram like this, so there is an overlap between the upper wavy line and lower wavy line right here, right between here and here, which means that those diagrams crossed. So if we consider no crossing diagrams, we only consider non-crossing diagrams, and this is precisely what I'm plotting right here. Suppose that's sum of all possible bubble diagrams like this, and I could get an infinite number of terms, and I could sum over all these terms in a geometric series. This is what people call this diagram equation, or a Dyson kind of a Green's function. So let's just stop right here, and next time we will sum over all this kind of ring diagram, and we form the Dyson equation like this. This is called ring because this is a ring. We have 1 ring and 2 rings and 3 rings and many rings, and we sum over all these ring diagrams, and this is what in solid state textbooks we call this RPA, random phase approximation. It's nothing but summing over all the ring diagrams, and each ring, remember, is nothing but sigma 1, and sigma 1 contains 2 sub-diagrams. The first one is a bubble, and another one is kind of a loop. Okay, great. So let's end our today's lecture, and we will continue tomorrow.